Okay, good afternoon. How's everybody doing? Yeah, super great. Okay, good. Okay, so we're going to be moving from Mars into the outer solar system to take a look at Europa's Global Geologic Map, which is a project I've been working on over the past year with Alex Patoff and Dave Sensky at JPL. This is one of my favorite pictures of Europa. It was taken by the Galileo spacecraft somewhere between 1997 and 2003 when it was in the Jupiter system. It was put together by Cynthia Phillips. And I really enjoy it because it really displays Europa's two very unique features. One being all of these cross-cutting dark lineaments that cover the surface, and the other being this lack of impact craters. There are no obvious impact craters in this image, and it's very odd for an outer solar system object, and this implies that the surface is pretty young, probably on the order of 100 million years or so. So we're going to be discussing these two things as we go through the Global Geologic Map. They'll come up many times. But first, a little background on Europa for those of you who might not be particularly familiar. It's about the size of our moon, so good-sized. It is one of Jupiter's 4 main moons, also referred to as the Galilean satellites. So it goes Io, Europa, Ganymede, and Callisto. Io, Europa, and Ganymede are in what we call a Laplace resonance. And this means that for every 4 times Io goes around Jupiter, Europa goes around twice, and Ganymede goes around once. And this is important because it keeps Europa in a slightly eccentric orbit. Without this resonance, it would circularize around Jupiter. This eccentric orbit kind of does what we see over here on the right. It causes Europa to flex as it goes around Jupiter, and or experience tidal forces. And so what this does is it creates friction within the body, which creates heat, and this is what we think allows Europa to maintain its liquid water ocean underneath the ice shell. Also, probably why it can form all of these very interesting features that we're going to, again, go over as we go through the Global Geologic Map. Okay, so first, this is the Global Image Mosaic of Europa, put together by the USGS, is the one in the background here. It consists mostly of images taken by the Galileo spacecraft, which was in the Jupiter system from 1997 to 2003. There are also some images that fill in the gaps that are still from the Voyager mission, so quite old data, really. We also have this patch over here, which looks a bit brighter. That's what we call colloquially the Super Mosaic. It was created for us by Jeff Collins. It includes a few more high-resolution images from the Galileo data, as well as just highlights albedo differences in this region. This image mosaic can create some challenges when trying to map the surface, and so I'm going to touch on 2 of those right now. One being the large variety of resolution of the images across the globe, and that's what's displayed here. You can see that across Europa, we are dealing with resolutions that vary from 200 meters to over 12 kilometers per pixel. And what that means is that we're going to have trouble maintaining a consistent map across the surface. Another issue that we always run into is the varying incidence angle. And what the incidence angle is just the angle between the sun and the surface. So at 0 degrees, that would be the sun directly overhead. And at 90 degrees, that would be the sun at the horizon. And this can affect the apparent albedo of features on the surface, or the apparent color of features on the surface. And this can, again, lead to difficulties when creating a consistent map across Europa. And these 2 things really arise from the fact that the Galileo spacecraft was not an orbiter. It was a flyby mission. And when you are just flying by objects, you fly by at different distances and have different viewing geometries. It's just a fact that that happens when you have a flyby mission. And this is just an example of actually what happens when you have different resolutions and different incidence angles. In the pink box here, we have an example of what happens when you are meeting 12 kilometers per pixel with 200 meters per pixel. You can see that some of those lineaments just completely die out. Where do you draw them? They don't go anywhere. You can't see them anymore. In the yellow box, we see an example of the incidence angle complications, and that's some of those low albedo features just turn into high albedo features. They turn from gray to white. And so again, this can create complications when trying to create a consistent map across the surface. So again, we'll take a look at the global image mosaic and just kind of orient ourselves here before I show you the global geologic map. So pick your favorite feature and look at it. Okay, so this, when it comes up, will be the global geologic map that we've created. And again, we've tried to address this consistency issue. We've had multiple people completely map the surface, and then we compare and create this agreed geology to have consistency and also objectivity, which is your goal when creating a geologic map. So we have 10 different geologic units that I'll kind of go through. They're paired into 4 different groups, and I have 8 different features, linear features and point features that we'll go through. But you can see off the bat, one of the main reasons we create global geologic maps is to really look at the global distribution of these features, and so you can keep that in mind as we go through. So first, we're going to start with craters. Craters are in our orangish colors. The crater itself is in that dark orange color. We have continuous crater ejecta in the medium orange color, and then discontinuous crater ejecta in the lighter color. And I'll show you examples of some of those different units here. So our continuous crater ejecta would just be the ejecta that's immediately outside the crater. It's heavily modeled, likely high albedo. Discontinuous crater ejecta is actually only found around 1 crater on Europa, probably the youngest crater, and this is Puil. And so discontinuous crater ejecta could be referred to as secondary craters or crater rays. And these will disappear over time due to space weathering or the radiation environment at Jupiter. And so this is why we think Puil is one of the youngest craters on the surface. And again, you can see there's about 40-something craters across the surface. That's astronomically low. For anyone who's looked at any other moon in the outer solar system, this is astronomically low. Usually they're saturated with craters. Like you can't even tell one crater from the other. And so this is why we think that Europa is probably about 100 million years old on the surface. So it has some sort of active resurfacing process that's erasing these craters. Next, so this might be kind of hard to see, but we're looking at the depression margins here, and they form great circles actually on Europa's surface, and they're also over here, and they're broad, shallow depressions, and they appear to be one of the youngest features on the surface because, and I've highlighted one here, because they don't affect the pre-existing structures at all, and they're really odd, really, and we don't really know what forms them. The only possibility that we've come up with so far is that they might be remnants of paleopoles from polar wander. So you can imagine that when you have an ocean underneath an ice shelf, the ice shell is rotating differentially from the ocean underneath. Your ice shell might rotate and change orientation with respect to the poles or the equator. So this could be evidence of that, not sure. Moving on, I think we're going to be moving to the chaos features next. So they take up about 38% or so of the surface, and we have 4 different geologic units to 4 different varieties of chaos. But chaos in general refers to a broken up terrain. It looks to be a broken up pre-existing structures that appears to be embayed by a matrixy material. And it's thought to be this is where the ocean, the underlying ocean, might be communicating with the surface, so which is very important for potential habitability. So they're of high interest to both the Europa Clipper mission and potentially the Europa Lander mission. So we have 4 different varieties here. We have a low albedo chaos, a high albedo chaos, a modeled chaos, and a Nobby chaos. Our low and high albedo, we actually, even though I've told you that that can vary due to incidence angle, we can actually quantitatively show that there are differences across the globe that are low and high albedo, and they are consistent. And then our modeled chaos here is just high and low albedo chaos right next to each other on small scales, so it's really patchy. And then we have an interesting occurrence of what we call Nobby chaos. And it only occurs in one place, in the southern trailing hemisphere of Europa. And it's interesting because it has a large-scale roughness and almost curvilinear fractures that run through it. And so it's just an interesting feature that we like to point out on the surface. Also, in our chaos here that I'm pointing out is our point feature, our 1 point feature that we have, and that's microchaos. And microchaos are these small, almost circular areas of potentially chaos. They're only 10 to 50 kilometers in diameter. So on our map here, they would only be represented by a point. And I'm going to try and make these show up a little bit better for you here. We map over 2,500 of them across the surface. So there's these little tiny green dots, if you can see them. And so we map over 2,500 of them across the surface. And it's actually really interesting because visually they seem uniformly distributed, which is not really something we would have expected. And something we're still exploring. So this is another great reason to create global geologic maps. You start realizing these things that you didn't know before. Next, we'll move on to bands. There are two types of bands, just a general band unit. And those are those long, dark, linear features that we were talking about before. And then we have a high albedo bands unit, which is down here at the bottom. There are only 2 of them, but they're very young and apparently fresh on Europa. So that's why we're highlighting them here. Bands are interesting because they're thought to be formed in an extensional process similar to mid-ocean ridge type spreading. So some good analog to something on Earth. And yeah, cool. Okay, so moving on, I think we're going to go through, the 2 different types of bands. So you can see we have a low albedo band and our high albedo bands, which are relatively fresh. And moving on, we'll be going to the linear features. And these linear features are scattered throughout the surface. We have 4 different ones that I'm going to highlight here. Ridges up here, which are just a long linear topographic high. And then we have cycloids, which are actually pretty unique and actually go back to what I was talking about in the beginning with that tidal forcing. When Europa goes around Jupiter, the stress field is rotating, and that's what creates these long arcs and cusps of the cycloids. And so something that's pretty unique to Europa. This doesn't really occur anywhere else. Troughs we have over here. There are just a couple of them, not very many on Europa. And then most commonly probably are these undifferentiated lineae outlined here in the pink. And that's because they're an artifact of the resolution. The resolution is just too low. We can't tell if it's a ridge or if it's a band. We just don't know. So it's undifferentiated. Lastly, we're coming to my favorite unit in particular. This is the ridged plains. So the ridged plains cover 55% of the surface, and I think they're really cool. Not a view often shared, but that's because at the global resolution, they don't look like anything. They don't look like anything. They're flat, they're white, they're not very interesting. However, when you look in the high resolution, the very few high resolution images that we have of Europa's surface, they're crazy. They're covered in all of these ridges crisscrossing all over the place, sets of them. We just have absolutely no idea what's going on. And this covers the surface. It literally covers the surface. So landing something on here is going to be interesting. So good luck to the lander people. I don't relish that job. Okay, so I'll leave you here going through what I just said. So chronostratigraphically, or kind of in order from youngest to oldest, we have our craters, our chaos units, then bands, and then our ridged plains being the oldest unit. But again, I like to emphasize this is only 100 million years of surface history. This is the visible surface history. Usually when you look at stratigraphic columns, you're looking at 4 billion years. This is just 100 million years. So a lot of surface history packed into 100 million years. And I'll leave you with these beautiful rotating globes made for us by Ashley Davies and take any questions.